Today we'll solve a very classic optimization problem about a ladder that we want to lean against the outside wall of our house, and it's supposed to reach over top of a fence to do that. And the question is, what's the shortest ladder that you can use that will be able to reach the house over top of the fence? Some dimensions you need to know is the ladder is resting on level ground, the fence is 6 feet high, and the fence is 4 feet from the wall. Now, something that needs to be said, we have to assume the wall is just high enough. If the wall is too short, then that'll affect the answer, but for larger heights, it doesn't really matter what the answer is. So we'll just assume that the wall is infinitely high, and that won't change the answer. To set up the problem, I'm going to start with a sketch of the side view. So I'm assuming that everything is perpendicular to the ground, except the ladder, which is at an angle, and the ladder just touches the fence. Otherwise, it wouldn't be the shortest ladder that we could use. I'll say that the ladder touches the house at a height of h. I know this distance is 4 feet. The height of the fence is 6 feet. I don't know how far the foot of the ladder is from the fence. I'll call that distance x. Now I have similar triangles, and I have this smaller triangle and this larger triangle. And the point is that corresponding sides of the smaller triangle and the larger triangle are in proportion. So I'll say that for the larger triangle, this height to the base is the same proportion as in the smaller triangle, which is 6 to x. Solve for h. The other relation that we have is that the length of the ladder, I'll call capital L, satisfies Pythagoras. L squared is h squared plus this side squared. And as usual, I'm expecting you to check this on your own time. Now, x can be anything positive. No restriction there. We can solve for L by taking the square root, but that's going to give us something ugly. And rather than worry about taking a square root, I'm just going to work with L squared. And the point is that if we're trying to minimize the length of the ladder, that's the same thing as minimizing the squared length of the ladder. Now, if you are not comfortable with this concept, don't worry, we'll do it a second way, and you can see why I'm preferring to do it this way. But if you think of the squared length as the more natural thing to try to minimize, that's equivalent to minimizing the length. Because the larger the length is, the larger the squared length. Minimize the squared length, you minimize the actual length. So if you think of the squared length as a variable, then here's the derivative. Find a common denominator and factor the top. So it works out a lot nicer than you might have expected. But that's the way we cook these problems to work out nicely. Now we want to minimize the length, which is the same as minimizing the squared length. So we look at the derivative and see when it's positive, negative, or 0. Well, it can't be, this can't be 0. Sorry about the x cubed there. So we can't make this 0, so we have to make this 0, which is that x is the cube root of 144. And for x between 0 and the cube root of 144, this derivative is negative, so L squared is decreasing. And for x bigger than 144 to the 1/3, the derivative is positive, so L squared is increasing. And it's exactly when x is the cube root of 144 that we get the minimum possible length squared, which is giving us the minimum possible length. That's feet, of course. Now I'm going to plug in this value into here, and then I find L by taking the square root at the very end. And I get something about 14.047 feet. And that's the minimum possible ladder. So I promised I would compare the alternative solution where we set it up as before, but then instead of working with the squared length, we go directly to the length itself. That's by taking the square root. It gets a little ugly, but no matter, when we take the derivative, all this ugly stuff ends up in the denominator, and what appears in the numerator is what we get from the chain rule. So it appears that the denominator is positive, so it doesn't really affect anything when you're looking when the derivative is positive, negative, or 0. The answer comes out just the same, and in either case, whether you do the longer way, remember you had to set it all up, so this really does get to be longer in the end. But whichever way you do it, remember that you have to justify why this gives a minimum length. I've justified it by saying for x less than cube root of 144, the length or squared length is decreasing. For x bigger than the cube root of 144, the length or squared length is increasing. So that means at the cube root of 144 feet, the length is minimized, absolute minimum.